Hello. So for 5.5, we're talking about calorimetry, and that suffix metry is measurement, and calor is heat, like a calorie or caliente, right? So this is how can we actually measure that energy? Basically, what we're figuring out is how did we get those delta H values that we saw in the last section, right? We saw that when we burned methane, it released 890 kilojoules per mole. Well, how do we get that? How do we know that? And there's actually many ways that we can figure that out. This is a laboratory technique where you measure we can't directly measure the amount of energy that the reactants lost, but what we can rather easily measure is how much energy the surroundings gained. And if we do that, and we know that the energy lost by the system is equal to the energy gained by the surroundings, then we can figure out what was the enthalpy of the reactants at the beginning, or the change in the reaction. So in order to do that, we are going to need to use a formula. And it is this formula right here. It's on your equation sheet. Is a really important formula. You will need to learn this. It's that Q, or delta H, right? Those can be interchangeable if we're talking about constant pressure, is equal to mc delta T. M is mass, and delta T is, of course, change in temperature. And one thing to remember is that change in temperature, that Kelvin and degrees Celsius would be the same. So if something is increasing by 25 Kelvin, it's increasing by 25 degrees Celsius. So all you need to do is, do final minus initial, and you don't need to worry about Celsius, converting Celsius to Kelvin, because the change is always going to be the same. Because remember, the Celsius scale and Kelvin scale are the same. We just moved 0 to a different place. So the piece in this formula that you do not know yet is this C. C is heat capacity, capital C. And so think of capital C for capacity. What it is the amount of energy needed to raise a sample of substance 1 degrees Celsius or Kelvin. So if you think about this concept that, when you put, let's say anything, you're cooking anything, you put it in the oven, the different substances that you put in the oven are all absorbing the same energy, but their temperature is not always changing the same. So you may see that, the metal will oftentimes get really, really hot in an oven, whereas the cookies will be not as hot, or if they contain a lot of sugar, it may be very hot. The temperature change is not always equal to the amount of energy that is absorbed. One example that we talk about this with is if you go to a beach, everyone's under the same sun, so everyone is absorbing the same amount of energy. But, the metal rim of your beach chair could actually burn you. The black top in the parking lot will burn your feet. But a towel gets warm, but it doesn't get hot to the touch. And then think of the ocean has been under that sun all day long. And the ocean, especially in New England, never really gets all that hot, even though it bakes under that sun day after day after day. So different substances will convert energy into a temperature change at a different rate, and that's heat capacity. Now you'll see 99% of the time we will use something that's called specific heat capacity. Specific heat capacity is specifically for 1 gram of a substance. So that's what that subscript S is in that formula there. It does not, I believe, appear like that on the formula sheet, but it does in our textbook. Here's a table of just different specific heat capacities for different substances. And the one thing that really stands out on this chart is just how large water's is. The fact that water has such a large specific heat capacity is super important. That's one of the reasons why it stays a liquid over such a wide range, which is very important to life existing on this earth. It's one of the reasons why temperature is much more stable in coastal areas than in the middle of the country. If you've ever traveled to, and Chicago is a great example of this, even though it's right by a Great Lake. Chicago's temperatures in the summer are hotter than us, and Chicago's temperatures in the winter are lower than us. And it's about the same latitude as us. And one of the biggest reasons, especially coastal Massachusetts, is because we have this giant ocean next to us. So in the summertime, it helps to cool us down. In the wintertime, it helps to warm us up. So water having a very high specific heat capacity is really important. Absolutely. So these, the math, like I said at the beginning, the math involved in this chapter is relatively simple. It is formula, plug it in, solve. And so if you do that, you will get all these answers right. The big thing is going to be the units, making sure that the units work out. So sample 5.6, how much heat is needed, so that's delta H, to warm 250 grams of water from 22 degrees Celsius to 98 degrees Celsius. So basically how much energy is required to, make a cup of tea. So the first thing we do is write the formula. The order that I learned it in is MC delta T. So I always learn it as like MCAT. Okay, M, mass, 250 grams. The specific heat capacity of water is on the previous page, 4.18. Look at the units for this. Joules per gram times Kelvin. Ooh. So joules per gram times Kelvin. So look at where the gram is in the denominator. And then my Kelvin, these are in degrees Celsius. I do not need to convert these to Kelvin first, because remember, a temperature change in Kelvin and Celsius is the same. So 98 minus 22, that is 76. So 76 Kelvin. And making sure that my units are going to cancel out. The gram is in the numerator and the denominator. Kelvin is in the numerator and the denominator. I multiply these out. I get 79420 joules. It's just asking how much heat, so I don't need to worry about should I keep this in joules or move it into kilojoules. It doesn't matter. But one thing I do need to pay special attention to is significant figures. So this guy should be 79,000 joules, or quite frankly, we use kilojoules way more often, or 79 kilojoules. Second part of this says, what is the molar heat capacity of water? So sometimes some tables will give you a molar heat capacity instead of a specific heat capacity. All that means is that instead of multiplying by the number of grams, you would just multiply by the number of moles. So if it's 4.18 joules per gram dot Kelvin, the molar heat capacity means that we need to change that gram into a mole. So I would need to 18.016 grams of water is equal to 1 mole of water. If I do that out, right, my grams units cancel, and I would be left with 75.3 joules still in the numerator, moles dot Kelvin in the denominator. Okay? Just following along with the units. Here's a multiple choice question. Suppose you have equal masses of two substances, A and B. When the same amount of heat is added to the samples of each, the temperature of A increases by 14, where the temperature of B increases by 22. Which of the following statements is true? So if you think about if one, A increases by less, so that means that it took more energy to raise the 1 gram of a substance 1 degree Celsius because it only went up by 14. So that's how I'm going to know that A has a larger specific heat capacity. I can also think of it this way. If this is X is the amount of energy that's being added, and this is the specific heat of A, M would be the same, and delta T was 14. And then if the same amount of energy, specific heat of B, the mass would be the same, and then this was 22, right? If these two would have to be the same, does it make sense that in order to make this mathematically correct, the specific heat of A would have to be larger than the specific heat of B? So the heat capacity of B is greater than that of A. The heat capacity of A is greater than that of B. That's true. Let's look at the other not right to sort of work through this. The molar heat capacity of B is greater than that of A. Well, we don't necessarily know because the question is asking about the specific, B is the specific heat because it says equal masses. If it said equal molars or equal moles of it, we could maybe talk about molar heat capacity, but since we don't know what the substance is, we just don't know. The volume of A is greater than that of B. Volume is not a part of this. The molar mass of A is greater than that of B. Again, we don't know that information, so B's the right answer there. Practice exercise 2, and this is a part A and part B. With these, please feel free to pause the video, then do some work, and then you can check your answers after. So large beds of rock are used in some solar heated homes to store heat. Assume that the specific heat of the rock is 0.82 joules per gram times Kelvin. Calculate the quantity of heat absorbed by 50 kilograms of rock if their temperature is increased by 12 degrees Celsius. So the question is asking me to solve for delta H. I know that's going to be MC delta T. The mass, because this is in grams, I'm going to need to put grams in there. If it's 50 kilograms, now 50.0 kilograms, you do not need to always do this out as long as you are always getting it right. So 50 kilograms is 50,000 grams. C is 0.82 joules per grams times Kelvin. I'm noting that that's only two significant figures where 50.0 was 3. And then the temperature is increased by 12.0 degrees Celsius. Again, the degrees Celsius and the Kelvin, that's totally fine. They're going to cancel out because a change in degrees Celsius and a change in Kelvin is absolutely the same. The grams are going to cancel out. So I just multiply these together and I get 492,000 joules or 490 kilojoules, right? Just two significant figures there. To make this right with significant figures, I can actually make that a 0. But yeah, so formula, plug it in, solve. Pretty straightforward. B, same scenario. What temperature change? Okay, so now it's asking me to solve for delta T. Would the rocks undergo if they emitted 450 kilojoules of heat? Formula. Delta H, I know, is 450 kilojoules. The M is that same 50,000 joules, not joules, 50,000 grams. The C is that same 0.82 joules per gram dot K, and then there's my delta T, right? Multiply those two together, then take 450 divided by that, and you get 11 Kelvin, right? 11 Kelvin should be the delta T. Okay, so that is, using that formula, that's the basics of what specific heat is. And now what we're going to do in the next video is actually use specific heat in that scenario that I talked about in the beginning of this video. The idea that we are going to measure what happens to the surroundings and then infer through a calculation what then happened to the system.